and other gases are good insulators, but they have their limits. In this lecture, I'm going to explore the electrical insulating characteristics of gases. Our understanding of gaseous insulation spans more than 100 years. A fascination with visual discharges can be seen early in old texts such as this one from the Royal Society. Back in 1880, two people, Spottiswoode and Moulton, went through extensive efforts and demonstrated a large variety of electrical discharge patterns that could be observed inside of evacuated tubes. About the same year, in another volume, de la Rue and Muller looked more to the interior and tried to, of their gas vessels and tried to determine what it was that influenced the electrical insulating characteristics. I'd like to quote from one of their papers. Nevertheless, it would appear that the law of the hyperbola holds equally well for a constant pressure in varying distance as it does for constant distance and varying pressure. The obstacle in the way of the discharge being the number of molecules intervening between the terminals up to a certain point. That's from 1880. This is the beginning of our understanding of electrical insulation. The two key ingredients are already barely visible, at least, in this initial work. These essential ingredients were more closely examined and, in fact, put in better perspective 9 years later in the thesis of Paschen. In this work, he, through careful experiments, showed that the product of pressure times gap distance determined the breakdown voltage for a number of different gases. His tables show this quite clearly and over quite a broad range of parameters. From a practical point of view, however, in the same issue, 1889, Max Wolf made experiments in another vessel which was pressurized. And in this case, he experimented with different gases at pressures to as high as 5 atmospheres. And he pointed and was able to show the very important fact that the breakdown voltage increased linearly with pressure. That is, higher voltages could be maintained if one continued to increase the pressure of the gas surrounding the electrodes. In the intervening years to the present, many investigators have re-examined this and have further elaborated on these basic fundamental characteristics. Retrospect makes it a lot easier to recognize that these were the key, in fact, the key ingredients. Modern day machines make use of this information. For example, this machine has its high voltage element surrounded by a vessel. The vessel is sealed, the air is removed, and another superior gas is replaced into the volume and, in fact, pressurized. In this way, more than a factor of 10 increase in insulation strength can be obtained compared to that in open atmospheric air. So we've seen that excessive voltage causes gases to break down. The greater the pressure between the electrodes, the greater the number of molecules, the higher that voltage becomes. We can continue that in both directions, both to higher pressures and to lower pressures. And in doing so, we formulate what is known as the Paschen curve. The basic feature that the insulating strength of a gas increases as the product of pressure times gap spacing is increased is seen in this figure. Voltage is plotted against that product, and in the gaseous region there is a monotonic increase of breakdown voltage. If the pressure or spacing is decreased, the number of molecules in the space between the electrodes becomes fewer, and eventually a minimum is reached in breakdown voltage, termed the Paschen minimum generally. And below that, the breakdown voltage rises quite rapidly. This rise in breakdown voltage reflects the fact that there are too few molecules in the intervening space to support an electrical discharge, and the vacuum region is approached. In the other direction, where the pressure times gap spacing is increased, the number of molecules becomes greater and greater, and the breakdown voltage becomes greater and greater until a saturation is reached somewhere in the liquid region. This general characteristic is common for various gases and describes in a very simple way the overall features that we see in gaseous insulation. A plot of collected data for nitrogen reveals the numbers associated with this type of figure. The voltage will typically range from 100 volts or several hundred volts at the Paschen minimum to the region of several 100,000 volts in the vacuum or high pressure range. At the same time, the pressure times gap spacing is changing by about 5 orders of magnitude. Now, the figure you see for nitrogen can be repeated for other gases, and it will look very similar, although the exact numbers will change slightly. Normally, however, the maximum and the minimum are quite similar once you go to the extremes. This region of the Paschen minimum also allows us to interpret the basic mechanism involved in the development of electrical discharge in a gas. We can interpret that in this vicinity, energy is efficiently coupled from the electric field to the gas molecules, as opposed to the extreme regions where that coupling is much less efficient. The process involved in this transfer of energy is principally the electron avalanche. Free electrons, which are present in the gas, are accelerated by the electric field, strike other molecules, liberating more free electrons and ions. These electrons travel, creating more ionization until a gas discharge is developed. The efficiency of that electron ionization is very high, and avalanche growth is very high in this vicinity of the Paschen minimum. The impedance to the development of electron avalanche is the same thing as saying we are impeding the development of an electrical discharge. The number of molecules in the space between the electrode controls that process, and therefore it is the density of the gas which is significant in defining the breakdown voltage in the gaseous region. The collected data for a number of different gases reflects this dependence on density. In the figure that you see, the breakdown gradient, the voltage per unit path that can be supported in a gas, is plotted versus the density of that gas for a variety of gases, in fact 4. The range of density extends from fairly low values to even the liquid state. And we can see this increase in insulation strength that accompanies an increase in density. The surprising feature may be to some that different gases all have essentially the same basic insulation strength when considered on a density basis. That is, from this figure, we can see that SF6 and helium both have approximately the same strength when measured at the same density. This is contrary to measurements made at constant pressure. In that case, SF6 has been found in some cases to have 16 times the strength of helium, again at constant pressure. So it is the number of molecules that impedes the development of a discharge and that impedes breakdown. To a first approximation, we can therefore say that it is the quantity of the gas and not the quality, not the type of molecule involved, which is really the inherent factor in the insulation of a gas. That statement, as well as the data that you've just seen, are based on results for relatively uniform electric fields, approximately parallel plate geometries. If there are non-uniform fields in which an avalanche can develop over a portion of the gap and then maybe decay over the region where the field is lower, then that strict formulation or relationship does not apply, and more factors have to be included. The influence of the avalanche growth can be controlled by having gap lengths which are too small, which in effect snubs out the growth of an avalanche, or can result from electrode radiuses, curvatures, which are too sharp, such that the field changes within the distance over which an avalanche grows. Those two factors, that is either too small a gap or electrode radius, produce an additive term to our relationships of proportionality between breakdown strength and gas density. This is first seen in relationships such as this, developed empirically, in which the breakdown voltage is proportional to the product of pressure times gap spacing, plus an additive term that accounts for conditions where the gap is very small. We can express that same empirical relationship for the density plot, in which the electric field is shown to be proportional to the density, with an added factor associated with gaps that are too small. When there is a small electrode radius of curvature, these relationships are sometimes expressed as similarity relationships, in which rather than having the gap as an additive term, the radius of the electrode appears. Nonetheless, in each case, what we're talking about is a density-dependent breakdown mechanism. For situations where the gaps are small or radiuses are present, we must include additional factors, but still it is density which is basically controlling the insulating strength. Another important ingredient to the insulation strength of gases or compressed gases is the duration for which the voltage or stress is applied. The reason this duration becomes of significance is because it takes time, like all physical processes, for the breakdown to develop. This means for a very short pulse, there is insufficient time for a breakdown to develop under identical conditions that a longer pulse would provide. Thus, we might expect that as we reduce or shrink the duration of time of an applied stress, the insulation strength of a gas will increase over that short period of time. This system that I am in front of here is a demonstration to illustrate some of these time-dependent effects. The upper electrode and the lower electrode form parallel plate geometries. The upper electrode is driven by an electrostatic generator to potentials on the order of 100 kilovolts. I have mounted inside and connected to the lower grounded electrode a spherical ball which is grounded via this bar to the edge of the lower ground plane electrode. And if I energize the upper electrode by turning on the generator, We will, as the upper plate charges, the generator is a low current, about a microampere. Every once in a while, as the voltage gets high enough for that gap to fail, see a spark breakdown. If I now introduce a second gap into this same electrode system, immediately under the spherical electrode, I'd like to explore the influence of that arrangement. Essentially, I still have this central spherical electrode at DC ground potential. Now when I turn on the generator, raise the upper electrode in voltage, I again see sparks between the upper gap. That is, from the upper electrode to that central sphere. The sphere being at ground, DC ground, that's exactly what we would anticipate. However, if I reduce the size of this lower gap to a significantly smaller value, and I'll do so by taking out just one of these supports. So now that smaller gap is on the order of a millimeter, and now energize it just as I have done before, the upper gap will again fail when the voltage gets high enough. But you see, besides the upper gap failing, simultaneously the lower small gap also breaks down. This occurs even though that central rod is at ground potential, DC ground potential. How is it then that this lower small gap is actually breaking down? The reason is that ground rod is acting like a transmission line. It's a very short transmission line, about 3 feet long, and therefore the duration of the pulse between the moment when the upper gap fails and the time until that ground is seen by the lower gap is the round-trip transit time of the traveling wave, on the order of 3 nanoseconds. So in this case, we are seeing that lower gap is breaking down in a mere time of only about 3 nanoseconds, the wave propagation time back and forth across that. If I now introduce one more change to this same arrangement, and that is replace this support rod, which is an insulator, with another support rod, which is a conductor. And I'll do so simply by sliding it in here. The significance of this change is that the distance until this support rod is now very much shorter than the previous one. I can therefore say that the duration of the pulse seen on that second gap is very much shorter than it was when there was an insulator in there. In this case now, we anticipate that the upper gap will fail, but no longer will a small lower gap fail. That is, we have reduced the duration of the pulse from several nanoseconds to something less than 1, which is insufficient to break down the gap that you can see there. This demonstration reveals the short time dependence, or the short time involved in the development of a discharge, and thus the time scale that's of significance for gas breakdown at high stresses. Now, what we'd like to do is see how general this is. And in the figure that you see on your screen, there is a plot which describes the electric stress as a function of the density of the gas versus the duration of the voltage times the density of the gas. And we see that there is a continual rise in stress as the duration of voltage is reduced at constant density. Or if you keep constant time, you can reduce the density and see that the stress or electric field to density ratio continues to climb. There's another ingredient that is important to point out in this figure, and that is that there are two curves in reality here. There's the solid curve, which extends across most of the gap, and then a fairly short one, mainly to the right. That short one is data obtained when there is no external irradiation of the gas gap. The solid curve applies when there is intense irradiation of the gap. The difference between these two curves relates to the duration of time that we must wait for initiation of the breakdown. The origins of the time delays that we've just seen arise from several different factors. Firstly, we must initiate the breakdown process. The wait for that initiation constitutes a certain amount of time that's dependent upon a wide variety of different mechanisms. Secondly, once we've even initiated a discharge, or the start of a discharge, that discharge must develop to the point where it bridges the gap. So there is the possibility that a delay will arise because after an initiation, the discharge did not completely develop, and another wait for another initiation must take place. Finally, a third factor is that once you've initiated it, it's developed sufficiently, the formation of the actual conducting channel must take place. Each of these takes time, and the amount of time depends upon the pressure and of the gas that we're using. We've seen a dependence on the product of pressure times time in the insulation strength. That dependence is the result, or may be viewed as a result, of the avalanche growth mechanism. That is, the dependence on these two particular parameters, pressure and time, the product of them being significant. If we consider that avalanche growth to some number, the natural log of the final value versus the initial value, as being in the numerator, and the mobility of the electrons and their ionization rate in the denominator, this relationship can be derived. This is independent of pressure. We assume that is that once a certain amount of growth has occurred, the breakdown develops. But the mobility is dependent on other factors. In fact, it's dependent upon the ratio of the electric field to the pressure, E over P. Mu is dependent upon E over P, and the net rate of ionization in the gas is also dependent on E over P. We therefore interpret that an electron avalanching process will result in a dependence of the pressure times time of a gas on the ratio of the applied electric field to the pressure. The two key ingredients that we've just seen, the pressure and the time to the insulating performance of the gases, in practice are modified by other factors. This transmission line will help me explain to you these additional elements to consider. Besides the gas and its density and the voltage that's applied, the electrodes themselves, the surfaces of those electrodes, can influence the electrical insulation strength through the asperities and surface irregularities that may exist. In addition, there may be contamination in the line, such as particles, which will initiate the failure of a breakdown at a premature level. And finally, there is solid insulating supports necessary to insulate the high voltage elements in the gas. These three factors, therefore, have to be included when we're trying to determine the ultimate insulating characteristics of a practical gas-insulated system. The electrode surfaces I was mentioning come in a whole range of different structures and features, having a significant effect on what the insulating performance will be. This piece of tubing has, just as it comes off the truck, scratches or whatever on it. These minute scratches make the surface irregular and can enhance in a local region the electric field and act to initiate breakdown at a premature value of voltage. You can make measurements with electrodes in test systems using full-size pieces or model electrodes. One of the questions you must decide is whether that surface is finished in a way that represents the practical application, or in fact maybe you're investigating to the best ability possible surfaces which are relatively free of irregularities, such as this polished piece of electrode. The problem, of course, is really defining what a real surface looks like. And it's a very complex structure full of hillocks and valleys, some sharp, some not sharp, all different types of radii of curvature. An example of that can be seen on your screen, where this scanning electron microscope view of an electrode shows an extreme amount of irregularities. If we try to model this or predict what is important, it becomes difficult, therefore, to characterize the surface accurately. So what people have done is to, instead of trying to polish the surface perfectly, is to place an imperfection that is well known and well defined on the surface of an electrode. This coaxial center conductor has such an imperfection. It's a small spherical boss sitting right at the very top here. That imperfection, in fact, becomes the site where breakdowns originate in practice. That is, it's the initiation site of a failure in a gas system when this is put inside and voltage is applied to it. We can use these known protrusions of known shape, known size, to accurately calculate the field distribution, the non-uniform field distribution, and therefore predict the real estimate of the amount of ionization and the breakdown potential that we would expect. You can see some results from a test in which a protrusion was added to a gap at several different pressures. In that results, there are 3 breakdown levels which coincide very closely to the inception, the calculated inception, based on this principle. Applying this initiation criteria to various electrode irregularities allows the comparison of different surface features. The figure on your screen illustrates this, where breakdown stress is shown versus the product of gas pressure times protrusion height for the case of SF6 gas. At low pressures and heights, the breakdown stress reaches that of a protrusion-free electrode, whereas at high pressures or high protrusion heights, the breakdown stress is reduced by an amount that's controlled by the shape and configuration of the protrusion. For very sharp point, the reduction is the greatest in comparison to ridge or dimples, in which the reduction is not very large. So we see that although a real surface is complex, it's very hard to predict, we can make a model for it and adjust the amount of insulation strength that can be sustained in a gas system once we've characterized the influence of these irregularities. And that has proved to be quite successful. So the influence of the electrodes and their asperites and surface irregularities can act to initiate failure in a gas. To account for that, we really, in some respects, must find the worst one. That is, the asperite that's the largest or the highest will act to be the one that triggers the failure in the gas. So there's a statistical nature associated with the surfaces and the surface structure, which compounds and makes more difficult the prediction of a particular failure voltage for any particular gas system. In fact, as you make the system larger and larger, the possibility of having a larger asperite exists, and hence we would expect that a larger area system would in fact have failures at a lower voltage level. This is the case, and as you can see in the figure on your screen, that it's a substantial factor to include. The breakdown voltage may be as low as 1/2 that of an ideally smooth electrode surface. So the amount of area of the electrode and its surface roughness and its features are elements that must be included in the reality of a practical system. The motion of a particle in an electric field arises from the charge that the particle acquires on one electrode and gives up on the other electrode. This charge is sufficient to elevate the particle and move it in this thing, in the interelectrode gap. The dynamics involved are an important part of what happens in a practical gas-insulated apparatus. That is, a particle, and certainly not a ping-pong ball, but a small particle will acquire a charge on one electrode, and as a result of the applied electric field, the combination of that charge and field produce a force which elevates the particle and moves it in the gap. Now, the motion will be even more complex than this round particle because the shape involved means it will bounce or ricochet in different directions. So particles will have a broader range of lateral motion compared to this in general. Furthermore, a complication arises when the particle isn't so nice and round as this one. For example, if I take this small spherical particle out and replace it with a particle of unusual shape, for instance, a piece of foil, which is large enough to see easily, again, something bigger than what we would hope to find in a practical apparatus. If we now turn on a voltage, the interaction of the field and that particle elevated again. But now, instead of traversing the entire gap, this particle is sort of suspended. It's sitting in between, or it's almost floating in between the two electrodes. The reason it doesn't cross the gap entirely is because the sharpness of it allows ionization of the gas. That ionization removes some of the charge at a rate about comparable to the amount that's arriving from the lower electrode. This means that this particle is now moving in a hovering state in which the emission from it exactly counterbalances the charge arriving on it. And so it stays suspended in the gap and will float. This is sometimes referred to as firefly motion. It's a further complication. It's very different from that was found or observed for spherical particles where there was no corona or ionization while the particle was partway through the gap. There was only the discharge right near the electrode once it had traversed. In this case, the sharpness of the particle allows it to move quite in another way. If I introduce one other particle at the same time, I hope, into this gap, this particle again being one which has a sharp edge and a blunt top this time, if we're lucky, we'll see that in this particular case, we weren't lucky, the particle will go to the upper electrode. And the only way to get that back is to remove it first. So we'll try once more. The only objective here being that we'll illustrate that that we can in fact have particle motion. It's stuck by static charge at either electrode surface as a result of this ionization process. And I guess it's not going to go. There it is. Okay, so for a moment at least, we observed a motion on the upper electrode. Here we see another motion at the lower electrode, which reveals still another pattern. That is, because of the shape of the particle, the emission is in one direction, and that causes the particle to rotate. This is sometimes demonstrated in science fairs as a coronal wind effect. It's the same influence. The important point here being, of course, that the particles, when they're small and the fields are high, such as occurs in a compressed gas environment, particles are elevated into motion. They're dynamic. The result of that is that the breakdown performance can also be dynamic in the sense that one moment or one measurement, the breakdown value is something, and then at another time it's quite different due to the change in the position of a particle. In a real piece of apparatus, the particles, of course, are not so large as what we've just seen here, and are a little more difficult to observe. Looking at the test facility that you've seen earlier, and taking movies through the port window while the system was energized and under compressed SF6 at several atmospheres, we indeed see each of these different categories of particle motion. That is, there's this bouncing or particles traversing the gap from one electrode to the other, driven by the electrostatic field and the charge they acquire. In addition, the type of motion which is governed by ionization of the gas in the vicinity of the particle, sometimes referred to as fireflies here, but in which the particle hovers near one of the electrode, is also very evident and can be seen. These movies also reveal another feature that can be employed in a practical apparatus, a technique to remove particles, a particle trap, an electrostatic particle trap in which holes or slots are provided in the outer electrode, which, if a particle enters, provides a low enough field so the particle becomes inactive. Particles, therefore, bounce by random motion at various locations, but when by chance they go into a trap, they remain there and are removed from their active influence in the gap, and hence the gap becomes cleaner and the insulating performance becomes greater. In addition, the reliability or the variation associated with a particle being at one point harmful and another point not harmful is also removed. So particle traps are a very effective means for controlling contamination. The strong influence of particles on the breakdown strength of a gas is depicted in the figure before you now. It shows the maximum reduction in insulating strength versus pressure measured in coaxial electrode systems with SF6 gas and 6 millimeter long particles. Because of the dynamic nature of particles we have just seen, where particles can move to or from sensitive regions, the specific breakdown voltage on any given test may fall anywhere in the shaded region from the top of the chart to the lower curved boundary. In summary, then, particles introduce substantial variation in the breakdown voltage of a gas. It is best to remove them initially or to introduce traps to collect them during operation. The influence of the solid insulating support on a practical system arises because of the distortion of the electric field that the solid insulating material introduces into the gas gap. The shape of the spacer, the solid material, each influences what that distribution will be. If the stress is enhanced at some area along the surface, we anticipate that ionization can more favorably occur in there, and therefore breakdown will take place. A variety of shapes of insulators have been used to try to demonstrate and establish that principle. That is, that by selecting insulators of different contours and some with different metal inserts, we're able to alter the electric field on the outside surface. Those that had a high electric field would fail at a lower voltage than those that had a lower electric field in the same system and at the same pressure, of course. In fact, to do this more carefully, we would pick a particular electrode geometry. In this case, we used a coaxial cable geometry, and these spacers were mounted radially across the gap. If we go to calculate the electric stresses that would occur, we can use a computer to map these field stresses in order to establish the relative intensities. This computer-generated plot, equipotential plot of a coaxial system with the center conductor here in the lower right-hand corner and the outer coaxial conductor from the left to top, contains a solid insulating support structure. The dotted line reveals the contour of that epoxy insulation. The dielectric constant in this case is 6. The fields are much more intense, as seen by the closeness or proximity of the equipotential lines spaced at 10% intervals in the vicinity of the central portion of the spacer. This higher stress means that breakdown is more likely to develop in that region. To each end of the spacer or support structure, the stresses become lower and lower, and in fact the triple joint, where the gas, metal, and epoxy all meet, is at a low stress, a favorable condition since this region is sensitive as an initiator of breakdown. So what we see, therefore, is that the design of an insulator and its particular shape and structure and composition are very important and a key element in the design of a practical power or other gas-insulated apparatus. Another factor that goes into it, which we've already discussed, particles, but now if you combine the problem of particles and solid insulators, you have even a worse situation, or potentially a worse situation. Particles, and I have a couple here on my finger, could be attached to the insulating surface and act to trigger the failure over a period of time or at some time during the course of operation. These particles intensify the fields on the surface, as they would in the gas, of course, itself. But they can accumulate over a period of time, and so instead of having just one particle, you may have many build up. And thus, over a period of time, the insulator surface would become worse and worse in its ability to withstand the stresses. Tests have been made to try to evaluate the influence of these particles. And you can see, for example, on your screen, a failure of one of the insulators here, which in a coaxial system at an elevated pressure of about 4.4 atmospheres of SF6. The failure originates at the particle and propagates to the center conductor and to the outer conductor. Because of the preferential directions of the fields, that propagation is non-symmetric, you can notice. That is, the discharge is following a path of least resistance, if you will, to bridge the gap between the center conductor and the outer conductor. Collected results obtained on several post-type insulators are shown in the figure on the screen. Surface flashover voltages triggered by 6.4 millimeter long aluminum wire particles are plotted versus SF6 gas pressure. The simple expedient of small changes in surface contour has not been found to greatly reduce the susceptibility to particles. Very large reductions in insulation strength can still occur whenever particles move to regions of high stress. To summarize then, the electrical insulation strength of a gas has at least two basic factors to consider: the density of the gas and the time at which the voltage is applied or the stress is applied. That density can actually be interpreted in terms of a pressure times gap length product for a specific type of molecule of gas. The time at stress is influenced by the wait for an initiation vent, the need for a critical amount of avalanche development, and finally the propagation of the discharge. These factors, the density, with some dependence on molecule type, and the time at stress, determine the maximum stress and stress distribution the gas will tolerate. More compact designs, allowed by use of higher gas densities and hence higher basic insulation strength, is accompanied by a greater sensitivity to disturbances. Even disturbances which are relatively small compared to the size of the gas gap can have a large effect. There is, in addition, these three major limitations for practical apparatus. We've seen the electrode surfaces, and their asperities and irregularities will act as initiators or potential initiators. They'll introduce breakdowns at lower voltages than can be expected for an ideal system, and in addition, they'll introduce a scatter or a statistical variation. That statistical variation means that one test might pass and the next test might fail. So it's a confusing factor that has to be incorporated into a practical design. Besides the electrode surfaces, there's also particle contamination. The contamination of different elements by different elements will mean that the sites of initiation will be present in the gas. We've seen that these contaminants can move in the electric field, and so that too introduces a variability, a system at one time that is operating very well, at another time, due to contaminant motion, will fail. Contaminant motion, that is, to a region of higher stress where initiation takes place. And then the solid support insulators necessary to hold the high voltage elements. These by themselves, if the solid material is proper and can take the internal stresses, amount to introducing exterior stress enhancements by their shape, by their relative dielectric constant, and by any embedded metal parts inside them that can alter the exterior fields. Note it is the stress enhancement in each case which is critical to the insulation strength, and the overall breakdown level is in accordance with the weakest link in the complete system. We're seeing in many ways that gases are well behaved, which is predictable from the point of view that if we understand the stress distribution and we understand the type of gas and molecule, then the performance that we will achieve can be fairly well predicted. So the two fundamental limitations and the three practical limitations that introduce variation are elements which have to be included in the design of gas-insulated apparatus.